Okay, so now we're going to talk about, we're going to continue working on the group theory problem number 5 from August 2013. So recall that F is a finite field with 3 elements, and SL2F, it denotes the 2 by 2 matrices of determinant 1. 2 by 2 invertible matrices of determinant 1 with entries from F. And in the last part, we determined that the size of SL2F was 24. And now we want to show that SL2F has a normal Sylow 2 subgroup. So recall from part A that the size of SL2F is of size 24, it has order 24. And so now if the number of Sylow 2 subgroups is equal to 1, then we're done. So let's suppose that it equals 3. So there's 3 Sylow 2 subgroups. Now, let SL2F act on the Sylow 2 subgroups of SL2F by conjugation. So this induces a permutation representation phi from SL2F into S3. And so by the first isomorphism theorem, SL2F mod the kernel of phi is isomorphic to the image of SL2F under the permutation representation phi. And this is a subgroup of S3. So because this is a subgroup of S3, and S3 has order 6, the size of the image has to be either 1, 2, 3, or 6. But also, SL2F is acting by conjugation on the Sylow 2 subgroups. And so by Sylow's second theorem, each of these subgroups is conjugate. So the size of, this action is transitive. And so the size of the image of SL2F under phi has to be either 3 or 6. It has to be greater than 2. So this eliminates 1 and 2 as possibilities. So now the normalizer of, so if I pick a specific P in the Sylow 2 subgroups of SL2F, the kernel of phi is contained in the normalizer of that Sylow 2 subgroup. And since the index of the normalizer of any Sylow 2 subgroup is equal to 3 because there's 3 Sylow 2 subgroups, and because this means that this forces the size of any normalizer to be of size 8. And so the kernel of phi has to be greater than 3. And then, so then if the kernel of phi is equal to 4, then the kernel of phi is normal inside of the normalizer of p. This is because this is 8 divided by 4, so the kernel is of index 2 within the normalizer, and so it's normal. And so the size of this is 2 of the normalizer of p mod the kernel, and since this is the smallest prime dividing the size, if SL2F is of order 24, and the kernel is of size 4, so the size of SL2F mod the kernel is 6. So 2 is the smallest prime dividing 6. So this means that the normalizer of P is normal in SL2F by the correspondence isomorphism theorem. And this forces the normalizer of P to be equal to P for every P. So P is a normal subgroup of SL2F, which means that because P is a Sylow 2 subgroup, that SL2F has a normal Sylow 2 subgroup. So then what happens if the size of the kernel is equal to 8? Well, then the normalizer of P is of size 8, and the normalizer of P contains the kernel. So this means that the normalizer of P is equal to the kernel. And this means that because the kernel is a normal subgroup, that the normalizer is normal inside of SL2F. This means, again, that P is equal to the normalizer. So then that means that P is normal in SL2F. So in all cases, we have that the Sylow 2 subgroup is normal inside of SL2F. And so hence, we've shown that SL2F has a normal Sylow 2 subgroup.